Good morning, dear students. In the previous class, we have derived the natural coordinates. The natural coordinates appeared as the area coordinates. We also derived the shape functions. The shape functions appeared as the natural coordinates, therefore, the natural coordinates are used as shape functions for a three-noded Cst element. Okay. Today we shall see the shape functions of the Cst element. For the Cst element, the shape functions are denoted by n1, n2, and n3. In the previous class, we learned that shape function n1 equals to L1, n2 equals to L2, and n3 equals to L3. Now what I do is I change my notations. Because L1, L2 and L3 are the natural coordinates, right? In place of L1 I use J. In place of L2 I use eta. Okay. Therefore, N1 equals to J and N2 equals to eta. Okay. Of all the three shape functions N1, N2 and N3, if N1 and N2 are independent, then N3 is dependent because N1 plus N2 plus N3 equals to 1 at any point on the Cst element. For any point on the Cst element or a three-noded triangle having the straight sides, sum of the shape functions is unity. Therefore, when n1 is assumed to be the coordinate, natural coordinate J, and n2 the natural coordinate eta, then n3 equals to 1 minus J minus eta. Okay. So therefore, instead of L1 for N1 and L2 for N2, I consider J for N1 and eta for N2 from now onwards, right? Then N3 equals to 1 minus J minus eta because sum of the shape functions is unity. Okay, right. We have a Cst element here. Observe carefully, it has three nodes. Cst element is a triangle having straight sides. Okay? With three nodes, 1, 2 and 3. This is the Cst element. Where 1, 2 and 3 are the nodes. The nodes are numbered counterclockwise. 1, 2 and 3. Okay, now here the n1 equals to J. The value of J never exceeds unity. And we know that n1 is unity at node 1. Therefore, J is unity at node 1. So this is, unit length. And n1 is 0 at node 2 and also 0 at node 3. Therefore, J is 0 at node 2 and it is also 0 at node 3. This is the reason why if you join this point with node 3 and node 2, the variation of the shape function n1 over the area of the Cst element, if you observe how it represents a plane surface. It represents a plane surface. Understand? Okay? Now, I see the variation of N2 over the area of the Cst element. Variation of N2 over the Cst element. Now, what is N2 here? N2 equals to eta. Therefore, at node 2, N2 is unity. And it is 0 at node 1. 0 at node 3. Right? Therefore, if you join node 1 with this point and node 3 with this point, see here, it represents a plane surface. Understand? Now, the shape function N3. Shape function N3. Let us see its variation over the area of the Cst element. The shape function N3 is unity at node 3 and it is 0 at node 2 and node 1. Therefore, if we observe the variation of the shape function N3 over the area of the triangle, how it represents a plane surface. And at any point on the Cst element, sum of the shape functions N1 plus N2 plus N3. At any point on the Cst element, sum of the shape functions N1, N2, N3. Sum of the shape functions N1, N2 and N3. If we determine which is unity, therefore, if you plot the value of N1 plus N2 plus N3 over the area of the Cst element, you get a straight surface parallel to the Cst element. A straight surface parallel to the Cst element at a height of 1 unit length. At a height of 1 unit length. Clear? Now, that is what we see here. N1 plus N2 plus N3 represents a plane at a height of 1 unit length. At a height of 1 unit length. At nodes 1, 2 and 3. Therefore, the surface is parallel to the area of the Cst element. Right? Okay. Now, because we use the constant strain triangular element for solving two-dimensional problems, the coordinates x and y are used to specify any point in the domain. Any point in the domain. And the same coordinates x and y are also used to specify any point in the Cst element. In two-dimensional problems, the domain appears as a two-dimensional domain. Therefore, to specify any point in a two-dimensional domain, you want two coordinates x and y. Hence, any point in the Cst element we can specify with the two coordinates x and y. And these two coordinates are converted into the coordinates j and theta. Hence, the shape functions are defined as the functions of j and theta. Clear? Therefore, N1 is j and N2 is theta. And therefore, N3 is N1 minus j minus theta. Where N1, N2 and N3 are the linear shape functions. Okay. Now, if you consider a Cst element, as I told in the previous class, any point in the Cst element divides the area of the triangle into 3 sub-areas. Now, if the nodes are numbered 1, 2 and 3 like this, the area opposite to node 1 is A1, the area opposite to node 2 is A2 and the area opposite to node 3 is A3. We know that the natural coordinate j represents the area coordinates, therefore j equals to a1 by a. Hence n1 is a1 by a. Now the natural coordinate eta represents the area coordinate, therefore eta equals to a2 by a. Hence n2 represents a2 by a. And coming to the third natural coordinate, here, the third natural for the third natural coordinate we are not using any symbol here, right? So once you define these two natural coordinates, you can define the shape function n3 as 1 minus xi minus eta. This n3 appears as the area coordinates, that is a3 by a. a3 by a. Right? In the previous lecture, the third natural coordinate, we learned that the third natural coordinate also appears as the area coordinates. What it is? a3 by a. Therefore, n3 equals to a3 by a. And when you sum up n1, n2 and n3, you get unity. Right? Now, isoparametric representation. We use isoparametric representation here to specify any point of the Cst element, using the shape functions n1, n2 and n3. When the same shape functions are used to specify any point of the Cst element, right, using the nodal coordinates, we say the formulation isoparametric formulations. The shape functions what we have derived are used to specify, to define any point in the element with respect to the nodal coordinates. We say isoparametric formulation. Therefore, what I do is I take a Cst element like this with nodes 1, 2 and 3, where the nodal coordinates of first node are x1, y1, and the coordinates of the second node are x2, y2. The coordinates of the third node are x3, y3. Okay. Now, I take a point of interest P here at the interior of the Cst element. Its coordinates are x and y. Now, to specify or to define the coordinates x and y, I use the same shape functions n1, n2 and n3. The shape functions what I have used to define the unknown displacement. The shape functions what I have used, to interpolate the unknown displacements with the nodal field variables. The same shape functions I also use here to specify a point in the Cst element. Right? So how we specify? I write x equals to n1 x1 plus n2 x2 plus n3 x3. This is how I define the x coordinate of the point P. X coordinate of the point P. Understand? And how I specify the point y? Y equals to n1 y1 plus n2 y2 plus n3 y3. This formulation what is called isoparametric formulation. Now in place of n1 you can put j, in place of n2 you can put eta, in place of n3 you can put 1 minus j minus eta. Similarly in this equation also. Okay. The same shape functions we use to define the unknown displacement fields. How? I say at each node there are two displacements. At each node there are two displacements. Right? in one of the previous classes, we learned that if J denotes the node, Q 2J minus 1 is the displacement in the direction of x-axis and Q 2J is the displacement in the direction of y-axis. Right? With this convention, I follow to specify the displacements of the nodes 1, 2 and 3. The node 1 has the displacement like this Q1 and the same node has the displacement like this Q. And node 2 has the displacement like this Q3 and the same node has the displacement like this Q4. 3 has the displacement Q5 like this and Q6 like this. Clear? Now, the point P considered at the interior of the Cst element has two displacements, say U and V. The displacement U that takes place in the direction of x-axis can be interpolated with nodal displacements taking place in the direction of same x-axis. How you can interpolate using the shape functions n1, n2 and n3. And similarly, the displacement V can be interpolated with the nodal displacements that occur in the direction of y-axis using the shape functions n1, n2 and n3. Therefore, we can write the displacement U equals to n1 q1 plus n2 q3 plus n3 q5. This is what I have written here. U equals n1 q1 plus n2 q3 plus n3 q5. And similarly, V equals to, what you write? V equals to n1 q2 plus n2 q4 plus n3 q6. V is the unknown displacement at the point of interest in the direction of y-axis. Therefore, to define the unknown displacement V acting at the point of interest in the direction of y-axis, we have to take the nodal displacements at all the nodes in the direction of same y-axis, and we have to interpolate with the shape functions n1, n2 and n3. That is what I have written here. V equals to n1 q2 plus n2 q4 plus n3 q6. Clear? Now, what is n1? It is simply J. What is n2? It is simply eta. And what is n3? 1 minus J minus eta. Okay? Therefore, here in place of n1 I write J. In place of n2 I write eta. And in place of n3 I write 1 minus J minus eta. In place of n1 I write J, in place of n2 I write eta, and in place of n3 I write 1 minus J minus eta. Then expand. Okay? So what we get here? J into q1. Okay? And here we get minus J into q5. Understand? Minus J into q5. Next. And so here what we get? Minus eta into q5. Okay. So therefore, when you take here J common, so what we get here? N1. What we get here? When we take J common, what we get here? Q1. Q1. So here N3 is 1 minus J minus eta into Q5. Okay. Therefore, minus Q5 into J. Hence I get here minus. It is not plus. Make correction. It is minus, not plus. The Q1 minus q phi into j. Next, plus. And here n2 is eta. Therefore, eta into q3. So you can take eta common because here n3 is 1 minus j minus eta. Right? And what is common here? Eta is common. When you take eta common, what comes here? q3 minus q phi. It is not plus. Make correction. Into eta. Okay? Plus q phi. You get like this. And coming to V, in place of N1 I put j, in place of N2 I put eta, in place of N3 I put 1 minus j minus eta. Therefore, when I take j common, what I get? Q2 minus Q6 into j. Plus, and here, when I take, eta common, what I get? Q4 minus Q6 into eta plus Q6. This is how I can represent the unknown displacement u and v in terms of the Shear functions using the nodal displacements. Okay, now in matrix form if we write, what we get? That we see. So here, we know that j is n1 and eta is n2. So therefore, I take the displacement matrix as the column matrix, having the elements u and v, which equals to, I take a matrix of unknown size. I say it is a Shear function matrix n, right? Into, now here how many nodal displacements we have? That we see here. There are 6 nodal displacements in this Cst element. Therefore, I define Q as the element displacement vector of size 6 by 1. Okay? This element displacement vector Q is a column matrix having the elements Q1, Q2, Q3, Q4, Q5 and Q6. Therefore, its size is 6 by 1. This is a matrix of size 2 by 1. This is a matrix of size 6 by 1. Right? Therefore, now this matrix what is size of this matrix n? It is simply 2 by 6. Size of the Shear function matrix is 2 by 6. So when you multiply n with q, you get an unknown displacement matrix, or a matrix with unknown displacements u and v of size 2 by 1. Okay? Now, the Shear function matrix n we write here. N is the Shear function matrix. Now, so here, what is Q? Q is a column matrix with elements Q1, Q2, Q3, Q4, Q5 and Q6. Now, so here, take this set of equations. Now, so N1 is multiplied with Q1. Right? Therefore, I put N1 here. And this doesn't have Q2 term. Therefore, I put 0 here. Now, this is the Q3 term. Therefore, I put N2 here. And this doesn't have Q4 term. Therefore, I put 0 here. Now, this is the Q5 term. I put N3 here. And this doesn't have Q6 term. Therefore, I put 0 here. Next, and I take this equation. Now, we have a Q2 term, therefore I put 0 here and I write N1 here because it is N1 into Q. Next, this doesn't have Q3 term, I put 0 here. And we have Q4 term, therefore N2 I write here. Next, this doesn't have Q5 term, I put 0 here. And we have Q6 term, therefore I put N3. This matrix what is called the Shear function matrix N of size 2 by 6. Of size 2 by 6. Okay, now I told you using isoparametric formulation we can describe or define the x and y coordinates of the point of interest P. Right? How we get like this? The same equations I have written here. X equals to N1 X1 plus N2 X2 plus N3 X3 and Y equals to N1 Y1 plus N2 Y2 plus N3 Y3. Okay. Now what is N1? N1 is J. We know that. N1 is J. Therefore I can write in place of N1 J. And what is N2? Eta. N3 is 1 minus J minus eta. Okay. Hence, when you take J common, you get x1 minus x3 here, plus, and when you take eta common, x2 minus x3 here, plus x3. And second equation, if you take, again, when you take J common, y1 minus y3 we get here, and when we take eta common, y2 minus y3 we get here, and then plus y. The same equations are written like this, introducing J in place of N1 and eta in place of N2, 1 minus J minus eta in place of N. Okay, now I use the convention. What is it? Say Xij equals to Xi minus Xj. That is what I have written here. This is the convention. And Yij equals to Yi minus Yj. With this convention, I rewrite the same equations. In isoparametric formulation. Okay, now how you write? X equals to x13 into J plus x23 into eta plus x3. Next, y equals to y13 into J plus y23 into eta plus y3. Here, x13 is simply x1 minus x3. Wherever I write, when I solve a problem, x13, I must understand that it is x1 minus x3. Similarly, x23, y13 and y2. Okay, right. Now, to determine the strains, partial derivatives of u and v are to be taken with respect to x and y. Why? What is the reason? The reason is, we know that u is a function of variables x and y. V is a function of variables x and y. And x is a function of variables j and eta. Y is also a function of variables j and eta. Okay. To determine the strains, u and v are to be taken with respect to x and y. Let us see why. Because epsilon xx equals to dou u by dou x. Epsilon yy equals to dou v by dou y. And gamma xy equals to dou u by dou y plus dou v by dou x. When you take a two-dimensional problem, the strains at any point are epsilon xx, epsilon yy and gamma xy. To determine epsilon xx, epsilon y and gamma xy, what you want? Dou u by dou x, dou v by dou y, dou u by dou y and dou v by dou x. Here, dou u by dou x, where u is a function of variables x and y. Therefore, we define u as the function of variables x and y and v as the function of variables x and y. And moreover, the displacements u and v are the functions of j and eta. The reason is x is a function of variables j and eta and y is a function of variables j and eta. Therefore, u and v are the functions of variables j and eta. Right? Now, using the chain rule for partial derivatives of u, we can write dou u by dou j which equals to dou u by dou x into dou x by dou j plus dou u by dou y into dou y by dou j. Next, dou u by dou eta equals to dou u by dou x into dou x by dou eta plus dou u by dou y into dou y by dou eta. Firstly, we take u, the displacement u, unknown displacement u. Later, we can take v also. This is how we can determine dou u by dou j and dou u by dou eta. Okay, now this set of equations, this pair of equations, we can write in matrix form. Here, a column matrix having the elements dou u by dou j and dou u by dou eta, which equals to a 2 by 2 matrix having the elements dou x by dou j, dou y by dou j, dou x by dou eta, dou y by dou eta into a column matrix having the elements dou u by dou x and dou v by dou y. Right? From this, what I want dou u by dou x and dou u by dou y. When I get dou u by dou x, what it gives me? It gives me simply epsilon xx. When I get dou u by dou y, where it helps me in determining the shearing strain gamma xy, because gamma xy equals to dou u by dou y plus dou v by dou x. When I get dou u by dou x, dou u by dou x helps me in determining the shearing strain gamma xy, because here I have dou u by dou. Okay, now this matrix dou by dou j of x, dou by dou j of y and dou by dou eta of x and dou by dou eta of y. Right? This matrix what is called Jacobian matrix or Jacobian of transformation denoted by J. Denoted by J. We say Jacobian matrix or Jacobian of transformation denoted by J. Okay? We had an expression for x. What is x? Using isoparametric formulation, we can write x equals to n1 x1 plus n2 x2 plus n3 x3. What is n1 j? Therefore, x1 j plus what is n2 eta? x2 eta plus what is n3? 1 minus j minus eta. 1 minus j minus eta into x3. Dou x by dou j we want here. Now dou x by dou j, if you determine, what is the first element here? Dou x by dou j. Right? Differentiate this with respect to j. What you get? X1. And here minus x3. According to the notation, say xij equal to xi minus xj. In place of x1 minus x3, I can write x13. Therefore, this is. Similarly, dou y by dou j. What is y here? Y equals to n1 y1 plus n2 y2 plus n3 y3. n1 is j, n2 is eta, and n3 is 1 minus j minus eta. Now, dou y by dou j. Dou y by dou j. What you get? You get y1 minus y3. Therefore, you can write y13. And similarly, dou x by dou eta and dou y by dou eta, if you determine, you get x23 and y2. The Jacobian transformation for a three-noded triangle. The Jacobian transformation for a three-noded triangle having straight sides. How I get? x13, y13, x23 and y2. Let us see. This is the Cst element. This is node 1, this is node 2, this is node 2. Nodes are numbered counterclockwise. Okay. What are the coordinates of this x1, y1? Coordinates of this x2, y2? Coordinates of this x3, y3? Okay. I say node 1 is the first node, and node 2 is the second node, and node 3 is the third node. This is my element node connectivity information. Element node connectivity information. When I consider node 1 as the first node, node 2 as the second node, and node 3 as the third node. How you write the Jacobian of transformation? x13, then y13, x23 and y23. If you write like this, 1, 2 and 3. Okay? x13, y13, x23, y2. Understand? Okay? Dear students, what we have learned in this particular class? We considered the shape functions as the natural coordinates because shape functions represent the area coordinates. Natural coordinates also represent the area coordinates. Hence, we have considered the shape functions as the natural coordinates. We have defined the unknown displacement fields, introducing the shape functions, right? And we have defined a point in the Cst element using Isoparametric Formulation, admitting the shape functions n1, n2 and n3, right? And we have determined the Jacobian of transformation. The Jacobian of transformation is a 2 by 2 matrix. It is a square matrix, right? This matrix depends on the coordinates of the nodes for a Cst element. The Jacobian matrix depends on the values of nodal coordinates of the Cst element. Okay, thank you.